Congratulations, you did that exactly right.
You don't need my help.
Now let's take a look at elastic collisions. So imagine we've got some ball here and another ball here. We've got mass 1, V1, and mass 2, V2, and they're coming at each other, and at some point inside we're going to have a collision. So here they're bouncing against each other. And since it's elastic, they're going to just bounce right off each other. And because it's elastic, the kinetic energy is conserved. So here we actually get two equations, two important conservation equations. The first one is that the initial amount of momentum must equal the final momentum, and the initial amount of kinetic energy must equal the final amount of kinetic energy. So we will get two sets of equations, which will be m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. And for kinetic energy, we get 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So we've got the system of equations, and let's say that we know the initial conditions. So we know V1 initial and V2 initial. What we'd likely want to find out are V1 final and V2 final. And since we've got two system of equations, since we have a system of equations, since we have two equations here, and we want to discover two unknowns, we're going to be able to do that. And so with a little bit of algebra, and I'm not going to go through the algebra. If you're interested in seeing it, just ask Mr. Kerrigan or ask me, or go on Mr. Khan Academy and Google elastic collision development. But with a little bit of algebra, we can get the following. Here are our equations that find the V1 final and V2 final in terms of the respective masses and then their initial velocities. And again, that just comes from solving those system of equations. Two important ideas to make sure that we are, or really one important idea with two things. So two important ideas. We've got kinetic energy is a scalar, so it's just a number, and momentum is a vector. So when we're dealing with momentum, it's very important to keep sign. Direction here matters a lot. So let's think about that in terms of two-dimensional elastic collisions. So the classic idea here, pool ball, we'll say, here's the cue ball, and we're going to hit it into, let's say that we're shooting at the 8 ball. And we'll call this M1 and M2, and this is coming in with some velocity, so V1 initial. And I'm going to write cue ball in here just so we know. Well, after they collide, let's say after they collide that the cue ball is going off at some angle. We'll call this theta 1. And the 8 ball is going off at some other angle. Theta 2, and here's our 8 ball. So what do we know here? Like, let's think about how we could try to think about what the velocity finals would be. So velocity final Q and velocity final 8 ball. Well, we know that the 8 ball had, I hope that you're familiar with this pool language and using it kind of expectantly. So here's our 8 ball. Our 8 ball, the initial velocity there was 0. So the initial amount of kinetic energy is just 1/2 the mass of the cue ball times V, I'll call this VC initial squared. C for cue ball. That's all of the initial kinetic energy. And the initial momentum equals MQ times VQ initial. And it's important to know that this momentum is all in the x direction. Let's consider a classic two-dimensional elastic collision. So we've got a cue ball that's going to hit into our 8 ball. This is a pool game. Hopefully you've all played pool at once in your life, and if you're hitting at the 8 ball, that means that you're about to either win or make a go at winning the game. So let's say we've got the mass of the cue ball, mass of the 8 ball. 8 ball sitting there, so the initial velocity of the 8 ball is 0, and this has some initial velocity going towards the 8 ball. And when we hit the 8 ball, the cue ball is going to bounce off at some angle to the horizontal, so we'll call that theta 1. And here's our cue ball. And the 8 ball is going to go off at some other angle, theta 2. And there it is. So if we want to find the velocity of the cue ball, the final velocity, and the velocity of the 8 ball, what we can do is use some of the ideas that we have. So the first one is that the kinetic energy is going to be conserved. And remember, kinetic energy is a scalar. So what we're going to get is that 1/2 mq v cue ball initial squared, and that's all of the initial kinetic energy because the 8 ball didn't have any, is going to equal 1/2 mass of cue ball times the final velocity of the cue ball plus 1/2 mass of the 8 ball times the velocity of the 8 ball, the final velocity squared. So that's one set of equations. The other set of equations is that momentum is conserved. And remember, momentum is a vector. So if we think about it in the x direction, my initial amount of momentum is just mc vci. And that's going to equal mc, the final velocity of the cue ball, cosine theta 1, plus mass of the 8 ball times the velocity of the 8 ball final, cos of theta 2. And the third equation I'll get is momentum in the y direction. So mass of cue ball times the velocity of the cue ball initially in the y direction. Well, that's just 0, because initially in the y direction it's 0. And so this should equal, and remember, think of that as like negative theta 2. Negative theta 2 there, but in cosine it won't matter. So then we get mc, so the mass of the cue ball times the final velocity of the cue ball sine of theta 1 plus mass of the 8 ball times velocity of the 8 ball final times sine of negative theta 2. Negative because it's opening up downwards. And so this result will be a negative value. And so now we've got, these are the three equations that we can have. How many unknowns do we have? Well, potential unknowns would be the initial velocity and the final velocities, and potentially their masses might be unknown. But using these three equations, we'd be able to solve for three unknowns. So here's an example of how we break things down into, when we're dealing with two dimensions, that we need to deal with kinetic energy as a scalar, but in terms of momentum, we need to break it up into its respective components.